Here we go, week 4, day 2, and we need to continue on. We've talked about sequences the last couple of class days, so today we're going to kind of wrap that in with a series. Often you'll hear people say sequences and series, so they almost always go together. The difference between a sequence and a series is that in a series you're always adding the terms that you saw in a sequence. So it's always adding the terms of your sequence. Okay? So if I'm adding the terms of the sequence, for instance, whenever we did, I don't know, the Don't Fence Me In problem, we had 6 bales of hay, and then we had 8 bales of hay, and then we had 10 bales of hay, and 12 bales of hay, and so on and so forth. That's the sequence notation that we would see. But here we're going to see the series notation, which is 6 plus 8 plus 10 plus 12 plus ... and it goes on until infinity or until I give it a stopping point. So if I gave it a stopping point of 206, because that was the 100 bales of hay, right? If I gave it that stopping point, then before that would have been 204, right? So let me say plus 204. Plus 206, and that's my stopping point. Okay, so you can see that in there. I can do interesting things in there. For instance, I know we've talked, I'm pretty sure we've talked before about the Gauss process, where he added the first and the last, and the first and the last, and the first, and kept on moving in, and did pairs. I know I did that in this class, I'm pretty sure. So you could do stuff like that, or you can use the lovely math notation, which is for summations. Summation notation. And you're going to see this in your homework, so I just want to make sure, if nothing else, you can read it and you know what that looks like. So generally this looks like the sigma sign, and it's capital sigma, and we go I equals A to B of F of I. Okay, that's how it's said. The sum of I from A to B, so I'm going to start down here low at A and go work my way up to B, where F of I is my function. So notations over here, A is my starting point. B is my ending point. And F of I is the function or sequence that I'm placing in, that I'm going to add up. And this little sigma, or the capital sigma, I should say, means add or sum. S-U-M, sum. That's what that means. Okay, so whenever you see those, you don't go crazy and whatever. So, for our purposes, the I is going to be the incrementing number. That's usually why sometimes they'll use that I, is because they'll say, oh, I'm counting this way. So for this sequence up here that I said, hey, let's change this into a series and add all of these things. Here it was a sequence. There it's a series because I'm adding it. I would say, hey, sum up all of the terms, and this would be from the first term, 1 cow, right? 2 cows, 3 cows, if you remember. This would be from the first term all the way up to how many cows? 100 cows, right? So from I equals 1 to 100, and then I'd need to have some way of relating back what that function was, or what that sequence was. Fortunately for us, we actually found it. It was 2x plus 6, right? So I could put in here 2I plus 6. Okay, so I have the function. This is what I'm sticking things into. Here's my incrementation, 1 to 100. And I can check myself because I can say, okay, I'm going to add the first term of this sequence. Well, what is that? The first term of the sequence, just focus in right here. 2 times 1 plus 6. Well, that was, oh, was that wrong? Oh. Yeah, I'm sorry. It was the first term was the 8 guy. Yeah, I totally lied to y'all. And nobody corrected me. You know why? Because you're not here to tell me. The first term had 8. I should have dragged out those notes, right? The second term, sorry about that, guys. The second term had 10, and the third term had 12. If I was really nice, I'd go back and re-record this video. But you're going to see I'm not always very nice because it's getting kind of late and I don't want to. So, love you guys. Sorry about that. Go back and make sure you've made that edit there. Sorry, the first term was 8, the second term was 10, and so on. Because remember the cows. The cow was in the middle. There were 3 over here. There were 3 over here. And then 1 under and 1 above. So the first term is actually an 8 because that was my cow in the middle. Okay, sorry about that. So this is the right formula. I just started on the wrong number up there. Okay, so first term, I'm going to stick that in there. It'll be, and I knew I was wrong up there, not here, but up there, because the first term should be 2 times 1 is 2 plus 6 gives me the 8. That's my first term, right? The second term will be 2 times 2 because I'm going to increment. I'm going to count up from 1 to 100. The second term is 2 times 2 because that's the next term. 2 times 2 is 4 plus 6 is 10. That's my second term. And so on and so forth and blah, blah, blah. But all the way up until I stick in 100, that's my top number, right? So 2 times 100 is 200 plus 6 is 206. And that's my 100th term. Okay, 100th term. So that would be what I would get as the sequence. So I know that this is generating the sequence, but the series is going to look like add, right? 8 plus 10 plus dot, 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 plus 204 plus 206. And I'm going to add all those up. So, and it would be nice if I didn't have to actually punch all that in my calculator, right, and say 8 plus 10 plus blah, 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 blah. So we're going to try to figure out today how can I do that without having to actually add 100 terms up and figure out what the series was. Because it was a big enough of a pain figuring out the general formula, right, so that I could get the 206. Now if I have to add all those up together, oh my gosh, it's just going to be a mess. So we're going to do a little bit of work and make sure we can all do this. First, before I give away the rule or the formulas or whatever, I want to do just a couple of examples and let you work through them. So I'm going to say example 1. I just want to make sure you guys can, I'm doing sigmas, I just want to make sure you guys can actually read the notation. So it looks like sum from I equals 1 to 5 of 4i plus 2. So I'm going to let you do that. And I'm going to say, okay, the summation, I'm going to add up. I need to figure out all of the first 1 to 5 terms. So I'm going to let you do that. I'm going to do it. You can kind of check me in a second, pause it, whatever. Make sure that you do it on your own and you can do it. Okay. So 4 times 1 is 4, plus 2 is 6, plus 4 times 2 is 8, plus 2 is 10, plus 4 times 3 is 12, plus 2 is 14, plus 4 times 4 is 16, plus 2 is 18, plus 4 times 5 is 20, plus 2 is 22. And by the way, inside of here you can see the sequence. There was a plus 4 in there, and you can see that was the constant rate of change, right? So everything that we've done so far should hopefully be kind of sort of tying in together for us here, so that you're like not thinking, oh my gosh, this is something totally out of left field. Everything should be working with us together. All right, so I'd like to be able to add all those up, and I'm just going to punch that on my calculator. That's going to be 6 plus 10 plus 14 plus 18 plus 22. Punch it in real fast. There we go. Equals a 70. Okay, that wasn't too horrible because I only gave 5 terms, and it was fairly small numbers, right? So we can still see the plus 4 is in there, just like we knew from the constant rate of change. All right, example 2. Try this one. The sum from I equals 2 to 5 of 3 times 4 to the I minus 1. Now this one's a little more complicated, so we'll do it together. Okay, so first thing that makes it a little more complicated is it doesn't want me to start at 1. It wants me to start at 2. Okay, so I'm not going to do the first term. I'm going to start on the second term. That's what it's telling me to do. And the second thing is that I've got this weird little adjustment step going on in my exponent up here. So whenever I stick in the 2, it's going to be 3 times 4 to the, but I'm putting in a 2. 2 minus 1 is 1. So I've got to do that little adjustment step in my exponent. So this is the second term. This is when I equals 2, right? So what's that going to be? Okay, it's going to be 12, right? 4 to the first is 4 times 3. Okay, plus, what's the next one? I is going to be not 2, but 3, right? So 3 times 4 to the 3 minus 1. I'll come back and do that in a minute. It's going to be 4 squared, right? Plus 3 times 4 to the next, instead of 3, I need 4. So 4 minus 1 plus 3 times 4 to the, instead of 4, I need 5. And that's my stopping point, so I need the 5 minus 1. But I'm not going to do the 6th term, right? I don't need him. I just needed to go up to the 5th term. So I know exactly how high I'm working my way up. Okay? Alright, but I needed to do something with that because it really kind of looks ugly. So my summation is going to be equal to 3 times 4, well that's a 12, plus 3 times 4 squared, well 4 squared is 16 times 3 is 48, plus 3 times 4 to the third, right? 4 minus 1 is 3. 4 to the third, I don't know what that is off the top of my head, so I'm going to do it on my calculator. Oh, I did know that. It was 64. 64 times 3, I actually cheated and wrote it down earlier, is 192. Check me and make sure. And then this is 3 times 4 to the 5 minus 1 is going to be 4. 4 to the 4th is, oh no, 256. Should have known that one too. 256 times 3 is 768. So now all that's left to do is add all of those things up. 12 plus 48 plus 192 plus 768. It's getting pretty big in here. It's 1,020. We should have probably known it was big because this was an exponential function, right? Right here was my exponential function. So my answer is 1,020, and that's a pretty big number. Again, inside of here, whenever I look, I can see this was times 4, right? Times 4, times 4. So I can see that that's the constant ratio going in there. So I can see that exponential, and the 4 was the base, right? So all those things we learned already should be adding up for me. So again, I know, hey, we're looking at a geometric sequence here. So, yay, all good. Okay, some formulas, because clearly this was just 4 terms in an exponential, and I'm already at 1,020. I really don't want to have to do that all the time and get these really big numbers and be like, oh my gosh, what's happening? So there are some formulas. The sum, and they're going to be split up by arithmetic or geometric, okay? So arithmetic, remember, was when I had a constant difference that I was adding to stuff. And geometric was when I had a constant ratio. So for an arithmetic sequence, the sum of the first n terms can be found by this formula, S equals n over 2 times a sub 1 plus a sub n. So we did a little bit of work with this notation a week or so ago. A sub 1 is my first term, if you'll remember. First term in the sequence. And a sub n is the general term, right? Or often it'll be the last one I'm asked for. So a lot of times that'll be what happens too. The general. And n is just going to be the number of terms. Okay, number of terms. Okay, and you should kind of recognize this formula. If not, I'm just going to tell you, put a big old star on it. It's Gauss's formula. If you haven't seen it in math history, it's coming your way. And also you use it in a lot of different places. So he kind of hangs out. And this one happens whenever I'm adding sequential terms, right? So a sub 1 plus a sub n. It originally came about when Gauss had to add 1 to 100. And he figured out it was 50 pairs. I think I talked about that a couple of weeks ago in here. All right, so this is Gauss's formula, and it can be generalized. And here comes an example. I think I'm up to example 3. Yes. Okay, and it'll go something like this. Find this sum. And it'll say stuff like the sum from I equals 1 to 50 of 3i minus 4. Now clearly I don't want to add up 50 terms of this thing if I don't have to. So I'm just like, hey, let's go in and check. If I had the first term, it would be 3 minus 4 is negative 1. If I had the second term, it would be 2 times 3 is 6 minus 4 is 2. If I had the third term, it would be 3 times 3 is 9 minus 4 is 5, and so on and so forth. And we can see there's a plus 3 going on in here. That's my slope or my constant rate of change, or however you want to think about that. Okay, so all of that stuff's still in there. It's not going away. Hope you watched the videos from last week, or else these will not make any sense. So I could do that, but gosh, I don't want to add up all 50 of those. So I can tell it's arithmetic because it's got this nice linear form going on here. I can see the plus 3's in there. So I would like to use the formula that I have, which again, S equals n over 2 times a sub 1 plus a sub n. Okay, that's what I would like to do. Okay. So if I could do that, if only I knew how many terms there are that I'm adding up here. Well, I already said it, 1 to 50, right? So my n here is a 50. So let's get some stuff over here on the side. N equals 50. If only I knew what my first term was. So a sub 1 is my first term. And hey, I figured that out just a second ago. I plugged it right there, right? So that's a negative 1. And if only I knew what the a sub n was. Now this is where I said sometimes we'll know that a sub n because we'll have a stopping point. Here it's a 50. If there was an infinity, then I would not have a stopping point, right? So it would go on for infinity. So just to be aware that sometimes those things happen. It's an infinite sequence, and I have a formula that I could use for those as well. So just so that you know, stuff happens. We can certainly come up with those. Okay. So I've got all of those. I just need to figure out what's the 50th term, right? So I may or may not want to actually figure that out. 50 times 3 is 150 minus 4. It's not too terribly bad. 146. If I can't come up with it, then I'll stick it on my calculator and figure out. But those are the 3 things I need for this formula, so here we go. S equals n is a 50. 50 over 2. It's going to be a 25 in a minute. First term is negative 1, plus the last term is 146. That's pretty easy math. Even I can do that in my head. That's good. Negative 1 plus 146 is 145. Hopefully I don't mess it up after I said that. And now I need to multiply 25 times 145, and I'm getting 3,625. So using my handy-dandy formula, I am able to add those 50 terms in pretty short order without having to do a ton of calculating in my actual calculator, like plus, 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 plus. So I don't have to keep up with 50 terms. I need the first term, I need the last term, and I need to know how many terms I'm adding. That's what I need in order for that formula to work. Okay? So that's for arithmetic. There's also one for geometric sequences, so we got to get that in here. I know. Stinkers. Gotta get those in here. For geometric sequences, there's a similar formula, but instead of the differences up here, we use the difference formula, the differences to come up with those formulas. Instead of that, we're going to use the ratios. So the sum, not sun, of the first n terms is, but you're going to know this one because you're going to see the r in there. You're going to go, oh, that's geometric. S equals a sub 1 times r to the n minus 1 all over r minus 1. And again, put that somewhere special because you're going to want it. On a test next week, I'll actually give you these formulas. So again, I don't want you to memorize stuff, but you need to know which one you're using. So again, here the r is the ratio, the n is the number of terms I'm using, and the a sub 1 is the first term, right? So the only thing new here is r equals ratio. What am I multiplying by over and over and over again to get that geometric, right? Okay, so example 4. Example 4 looks like, find the sum and that is sigma I equals 1 to 20. So again, they're asking me to find the first 20 terms here of 3 times 2 to the I. That's my formula I'm using. If I were to try to work that out, what am I multiplying by over and over again? Well, it's the 2, right? 2 is my base. So let's just get some numbers in there. 2 to the first power would be 2 times 3 is a 6, plus 2 to the second power would be 4 times 3 is a 12, plus 2 to the third power would be 8 times 3 is 24. So I can see this is times 2, right? Plus dot, 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 dot. And clearly I don't want to do 20 of those if I don't have to. And so what I really need to know is what's the 20th term, right? Because, well, actually on this one, I'm sorry, I don't even need to know that. On the arithmetic, I need the 20th term. So I don't even have to plug in the 20th term. I have a nice generic formula here that I'm going to use. So here we go. Sorry, let me scoot this up a little bit. Eek. There it is. Okay, so whenever I look at that, I say, all right, guys, I need to use this formula. My sum is going to equal my a sub 1, the first guy, I have that. I plugged it in already. I know what it is. That's a 6. Okay, I'm going to multiply that by the ratio. What's my ratio? My ratio is the 2. It's the number that I'm multiplying by over and over and over again. What's the n, number of terms that I'm raising it to? There are 20 of those. So to the 20th minus a 1. The 1 is in the formula. I don't have to do anything with that. Again, my ratio, what was that? It's a 2. And the minus 1 there is again in the formula. Okay, so I'm going to have to do a little bit of arithmetic, but we would expect this to be a pretty big number, right? So 2 to the 20th and all that stuff. Let me get my calculator out because I'm certainly not doing that all by myself. 2 to the 20th is going to be a really huge number, 1,048,576. So I've got 2 to the 20th. I need to subtract 1 because that's in the parentheses before I do my multiplying, right? So I subtracted 1. I'm going to multiply that by the first term, which was a 6. Still a pretty big number. That's 6 million. And I'm going to divide it by 2 minus 1. But hey, look, 2 minus 1 is just 1, right? So I don't need that. So this is actually my number. That's 6,291,450. Okay. So that is a pretty stinking big number, right? I clearly did not want to add those 20 terms together because that was going to be not fun at all. So don't do that. You're going to use that formula. You're going to see S stands for sum, by the way. Last week we had the A sub 1 and the A sub n. So those were just the terms. So those formulas last week were in order to find a certain term in a sequence. These formulas this week is the sum. So that's the series. So I'm adding things up. So those are going to be my sigmas and all that stuff coming in. Okay. So you just need to be able to learn that notation. If you can just read all the notation and understand how the particular formulas work and what you're substituting in for, I think it's not going to be quite so bad as you would think it would be, right? All right, so just some little notations, I guess, I want you to think about, or things to make note of. What happens if certain stuff is going on? So what if either the D or the R is greater than or equal to 1? Notice, if the D or the R is greater than or equal to 1, then the series will continue to get larger, right? So if my difference is a 1, then, or bigger, greater than or equal to 1, so if my difference is like a 3, then my series just keeps getting larger. 2 plus 3 is 5 plus 3 is 8, so on and so forth. If my ratio is equal to 1, then if it was 1, then it would be like 1 to the 20th power here, up here. And that wouldn't be a big deal, but I still got this other stuff here, and I'm multiplying by 6, so things are growing, right? If my ratio was greater than 1, then clearly things are growing. And if it was less than 1, what would happen if the ratio was less than 1? So here the answer is the series will get large, continue to get large. Okay. And if it was less than 1, that was the next question that I had. In particular, R is less than 1. Okay. Then I'm multiplying things like take a half, right? So if I took 4 and multiplied it by a half, I'll get 2. And if I take 2 and multiply that by a half, I'll get 1. If I take 1 and I multiply by a half, I'll get a half. Until sooner or later, I'm getting smaller and smaller. So the sequence will get smaller and smaller. Okay. The series, what will happen is we talk about all of my terms will get really close to 0. Terms get close to 0. So let me give you that example. Okay, so for instance, the one where I said, what if R equals 1/2? Okay, and we're going to start with a 4. It'll be 4, and then 2, and then 1, and then a half, and then 1/4, and then 1/8, and then 1/16, and then 1/32. Okay, so I just keep on multiplying by 1/2 over and over and over again. Okay, so I can see that my sequence terms are getting really small. So in fact, and this is a limit idea, so maybe you've seen this in 361 or 362, these get to where it's like I have that pie and I start cutting it up into little bitty pieces. If I have 1 pie and I cut it into halves, well, that's not a big deal. If I have 4 pies, not a big deal. But if I get to cutting 1 pie into 16 pieces, those start getting kind of small. Even if it's a pizza, 16 pieces are kind of small. 32 pieces, smaller yet. 64 pieces, which would be the next one, really small. And this just keeps on going forever, right? So I'm thinking this is going to get really close to 0. Okay. So in general, whenever I'm looking at a sequence, there's something that you can see. And in particular, I'm talking about an infinite sequence here, so we'll talk about that in a second. But you can see the limit as n goes to infinity. So if this bottom keeps on getting bigger and bigger and bigger and bigger, then of the r to the n, my terms are going to be getting closer and closer and closer to 0. That's the notation. If you were looking at it from a calculus point of view, you would see that particular notation. So as I start thinking about that, hey, all these terms are getting really, really small, right? Then I'm kind of curious, well then, what if I had did this forever, 1/32nd, 1/64th, forever and ever and ever, and sooner or later I'm at 1/1,000,000. Well, if I take that one little piece of pie, or that one pie, and cut it into 1,000,000 pieces and say, here's your little speck of pie, you can have that. You know, you're going to look at me and go, look, lady, that's ridiculous. You might as well just not give me anything because that's not a piece of pie. That's worth nothing, right? So you would say, hey, I'm at my limit. Don't give me that stinking pie, that little speck of pie, and call it a piece of pie. That's 1/1,000,000th of that pie. That's crazy. So anyway, we're going to have something that's called an infinite series. And so sooner or later, I'd like to add the sum of an infinite series, of course. You know, so what if I wanted to add all those numbers up? That's what starts happening, right? So we go, hey, let me think about this. I'm going to give you an example. Well, let me give you the formula first. So here's where that would come into play. You have to have numbers that are between -1 and +1 for your ratio, okay? Or you could think absolute value of r is less than 1, okay? So if I have those things going on with my ratio, then the sum of the infinite geometric series is again given by a formula, of course, they've got them. S is equal to a sub 1 divided by 1 minus r. So again, a couple of things are happening here. Instead of having, say, the number 20 at the top of my sigma, I'm going to see an infinity sign up there because it's going to be an infinite geometric sequence. And I'm not dealing with D's here, I'm dealing with R's, right? So these are geometric. So we're going to see that coming in. So here's an example. I think I'm up to example 5. Here's the mathiness of it. And unfortunately, I have seen some of these types of questions on the state exams. So the Texas board says, hey, y'all need to know some of this stuff. And in particular, they really want you to be able to use the notation and find a particular term and things like that. So find the infinite sum, and here's what it would look like. The summation I equals 1 to infinity, that's how you know it's infinite instead of a regular old series, of 2 to the, and I'm going to do I minus 1. Okay, so, I'm sorry, negative I minus 1. So what the heck does that negative up there tell me? Well, that negative up there tells me that my exponent is negative, right? Which means, what do I do with negative exponents? When I see a negative exponent, I put everything under 1 and make it into a positive exponent, right? So let's think about that. That really means, even though it presented itself as a 2 here, it was not. My r is really what's being raised up to this power, or you could think of it as this, right? 1/2 to the I minus 1. So r here is really a 1/2. So we have to be a little bit careful because sometimes they might sneak something like that in there. But I definitely see that my r is less than 1, right? So I'm going to fall into this range here. So because I'm falling in between -1 and +1, I'm going to use that formula. What do I need to use that formula? I need the a sub 1. What would that be? Well, let's think about it. I should have written these numbers up here somewhere. I'm sorry. So let's think about it. So we're doing 1, I equals 1 to infinity whenever I've got here, I lost my I equals 1 to infinity. I equals 1 to infinity. So I can't be losing that, right? So I equals 1 to infinity. So the first term is 1/2 raised to the 1 minus 1. Well, what is 1 minus 1? 0. And there's an exponent rule that says anything raised to the 0 power is just a 1, right? So that guy is a 1. Plus, and then the next guy is going to be 1/2 to the first, and the next guy is going to be 1/2 to the second. I don't really care about those. What I care about is the fact that my first term here is a 1. So I've got a sub 1 equals 1, and I've got r equals 1/2. That's what I need in order to be able to use this formula. Because the 1 there is part of the formula, right? I'm not going to do anything with it. So this looks like, okay, what's my a sub 1? Summation. Again, put a mark on it. A sub 1 was a 1 over 1 minus r. Well, what's 1 minus r? 1 minus r is going to be 1 minus 1/2, right? Sorry, guys. I must be getting tired. It's getting messy. Really messy. 1 over 1 minus 1/2 is 1/2, and 1 over 1/2, what am I going to do with that? Well, I don't want the fraction on the bottom, so I'm going to invert and multiply, right? Multiply it by its reciprocal. Whatever I do to the bottom, that needs to go away. It's a 1 on bottom. I have to also do to the top, right? Correct? So 1 times 2 is a 2. So double check me on my arithmetic there if you're not sure what the heck I just did. Dividing by a fraction, I don't want to just leave the fraction down there because it's a fraction inside of a fraction. That's really bad form. We can't do that in math. Nobody has a meaning for 1 over 1/2. But if we invert that bottom, multiply it with its reciprocal, then the denominators go away. And if I do the same thing to the top, I get 1 times 2, and that's just a 2. Okay? So what this tells me is, hey, look. Even though I've got this series, so what did we say it was? It was 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, right? And it kept on going. 1 plus 1 over 32 plus 1 over 64 plus ... Even though we've got this infinite series that's going on forever, basically I've got 1 plus 1/2 plus 1/4. Well, I know that's 1 3/4, right? But then these pieces that are fitting in keep on getting smaller and smaller and smaller. And when I look at that, I go, oh my gosh. So what you're telling me is the total sum is going to, the limit is getting close to a 2. That's what we just said, right? The summation is a 2. S equals 2. That's what we just did. So even though I have a 1 and a 1/2 and a 1/4, all these little pieces in here together, if I had a total box that was a 2 box, you know, 1 plus the 1 would be done. But if I add up all these pieces together in here, all of those pieces together are basically adding up to a 1. So it's 1 plus 1 gives me the 2. So even though I got all those pieces, it's infinite. It just doesn't matter because it's just adding to a 2 total. So that's kind of a different thing. It's that limit mentality. I've got that word thrown in there. Limit mentality. Hopefully you've seen some of that stuff before, but if not, you're going to get a little bit of a chance to play with that, and I'm going to give you an example in a second. So this video is not going to be as long as the videos from the first day. Okay, so example 6. Find the infinite sum. Sometimes we help you out in the directions and tell you it's an infinite sum. Sometimes we don't. Sometimes you just gotta know what the heck's going on. So they're actually giving me the numbers in the sequence. 3 plus 3/4 plus 3 over 4 squared plus 3 over 4 cubed plus ... Now, if you're not sure if it's an infinite sequence or an infinite series in this case, then the way to know is, do you have an ending point? If there was a plus ... and then I said, I don't know, 3 over 4 to the 10th, then you'd know you have a stopping point. But if it doesn't, ... means infinity, right? We're going way out there to infinity. Okay, so we got to kind of figure out what this is. And it would be nice if this thing didn't go to infinity whenever I add it up, because that would kind of make it worthless. So I need to kind of figure out what's happening each time here. What am I multiplying by? Because this looks geometric to me because I've got some exponent stuff coming in there. So here it was 3, and I multiplied that by what? Times 1/4, right? 3 times 1/4, put the 3 over 1, 1/4. Yeah, that's 3 on the top, 4 on the bottom, okay? And then I did times 1/4, and then I did times 1/4. And I know it's times 1/4 after that each time because the only thing that's changing are the exponents, right? And they're growing, so I know my R equals 1/4. That's what I know. Okay? So when I see it like that, I'm like, yay, I know my R is 1/4. Let me use the sum of the infinite series. It's geometric. I'm going to use that formula we just had a minute ago. S equals A sub 1 over 1 minus R. And again, you don't necessarily have to memorize. Gosh, I just need my first term because I've got my R. Well, we know the first term is the 3. We can do this. Okay? We can do this. Yay. All right, so S equals, the first term is a 3 over, the 1 is in the formula, 1 minus, and the R is 1/4. Going to have to do a little arithmetic here. It's okay. 3 over, this is going to be 1 minus 1/4 is 3/4. Please don't try to start messing things around and making decimals because most of the time, if I leave it as a fraction, things will work out in the end. So leave it alone. What do I need to multiply by on the bottom to get the denominator to go away? That's a 3/4. I need to multiply by 4/3, right? That's its reciprocal. That'll make it go away. I get a 1 on the bottom. But whatever I do the bottom of a fraction, I have to do to the top of the fraction. Let me write this guy out. I've got 3 times 4/3. The bottom went away. That's a 1. I'm going to write the 3 over 1 because sometimes this bugs people. That's a 12 over 3. Or if you saw it, you could have reduced right there, right? I don't care if you do it in which place, as long as you do it eventually. At the end, I reduced and I have a 4. Okay, so the sum of this geometric series, 3 plus 3/4 plus 3 over 4 squared, is a 4. Okay, I'm going to let you do one. It's going to be great. You're just going to have to think a little bit about what your R is. So example 7 says, find the sum. This time we're not being quite so nice to you. You'll have to figure out if it's a finite or an infinite series. It's 3 plus -1 plus 1/3 plus -1/9 plus ... So what do we think? I think it's infinite, first of all. So the only infinite series formula I have is for the geometric. So I'd like to think, oh my gosh, I hope it's geometric. I think I'm multiplying by something each time, but weird stuff is happening in here. I'm going plus minus plus minus. I think we've talked about this before. When I'm alternating, this means I was multiplying by a -1, right? This means it was -1 times -1, which gave me the positive. And then this was a -1 times a -1 times a -1, which gave me the negative. So something in my ratio has a negative in it is my point, right? So, because here I took a positive number, I multiplied it by something, I got a negative. Took a negative, I multiplied it by something, I got a positive. So I'm going to start out with R equals negative. That takes care of the alternating signs. And then what is it? And generally, I start on the first one. What did I multiply the 3 by to get to the -1? Because these are geometric. So first of all, it's negative, right? And second of all, I went from 3 to 1, which makes it smaller by how much? I could think I'm subtracting. I could think it's -4. But if you look right here, you'll see, oh, I go to fractions. So that means I probably divided. So 1, look here, 1 divided by 3 would give me the 1/3, right? In fact, -1 times -1/3 would give me a 3. Or I'm sorry, a 1/3. So let's see if that works here. 3 times -1/3 would give me a -1. Yeah, that's working. So these are all times. times 1/3 times negative 1/3 gives me a negative 1/9. Yeah, that's working. Okay, so my ratio is negative 1/3. So we're going to have to be a little careful with our negative signs. But that's not that big of a deal, right? We can deal with a stinking negative sign. No worries. Okay, so I'm looking at it and I think, okay, it's infinite and it's geometric and I have my ratio and I also have my A1, which I need for that formula that we had up earlier. A1 is a 3. The formula was S equals, let me scoot that up a little bit, A sub 1 divided by 1 minus R. My A sub 1 is a 3. 1 minus, be careful because it's minus negative 1/3, right? Because the 1 minus is in the formula and then the ratio is a negative 1/3. So that's 3 over, it's actually 1 plus 1/3. I'm going to do that as a fraction. 1 is 3 over 3, so this is 4/3. And the reason I'm doing it as a fraction is because I know I'm going to clear out that denominator by multiplying by 3/4. That's a 1. Whatever I do to the bottom, I need to do to the top. So real quickly, I'll rewrite that. 3 times 3/4. Is everybody okay with that? That's a 9/4. I'm going to leave it just like that. If you want to make it into 2 1/4, then make it into 2 1/4. It is not a whole number like the last couple that we had. So it's important that I know, hey, that's not really going to do anything nice and pretty. It is a ratio. I'm kind of running out of time. So I have an example 8. I'm just going to write it here. I'm going to let you think about it because this was a rational number. What if I had an irrational number? I'm going to give you one and you can play with it if you want to, or you can just see similar stuff in the homework. So this is find the infinite sum. Move that out of the way. Find the infinite sum. I know it's infinite because it's got the infinity on top. I equals 1 to infinity of, and the thing it gives me is 8 times negative 0.3. So this is a ratio, and this number is less than 1, right? And it's raised to the I minus 1. Okay. So let's think about that for a second. This is a geometric sequence, because that's the geometric look. It's not the arithmetic look. I know I'm multiplying, and I'm raising that exponent, so I know I'm multiplying over and over again. This is my base right here. If I was looking for that, I would know, hey, 0.3 in the base. So my R here is negative 0.3. Okay, so it's less than 1. So you're going to use that geometric sequence. You're going to figure out what's my first term. I want you to do that real quickly. I will just tell you what it is so that you can be sure you know. Whenever I put in a 1, the 1 minus 1 is 0. And so anything to the 0 power is a 1. So this is 1 times 8 is 8. So I'll let you know that, and I'm going to let you know that your sum should look like about, when you finished, 6.1538, and it just kind of is a decimal that just kind of goes out there. Okay. The reason I'm skipping that is because I want to make sure to get to this guy right here. So I want you to see what the heck is going on with this limit idea. So it's kind of a famous, and you know I'm not an artist, but it's kind of a famous pattern that happens. If we take a square, and hopefully it is truly a square, I never said that my pictures are perfect, and say it's a cake or something like that. And there was actually this problem that I've seen before that's like so-and-so's birthday cake. And somebody comes along and eats 1/4 of it. Okay? And then somebody comes along and eats 1/4 of 1/4. And then somebody comes along and eats 1/4 of 1/4 of 1/4. That's kind of the idea. Okay? So somebody takes out 1/4. The shading process is going to go on forever and ever and ever. So somebody else takes out 1/4 of 1/4. That would be 1/4 of 1/4, right? And then somebody comes along and takes 1/4 of 1/4 of 1/4, and so on and so on. So this is a pretty famous type of problem, and you can see there's a pattern that's kind of happening in here, and you can see that inside of here these pieces are getting smaller and smaller, but the interesting thing is that the shading goes on forever. Okay, even after it's too small for me to physically show you what the heck's going on in there and do that kind of thing, it's still there, right? So if I wanted to look at that, I could say, oh my gosh, you know, that's a series if I added those up, right? So if I add them, add the shaded parts, if we assume that this is a whole entire thing, then that first piece, like I said, was 1/4. And then the next piece was 1/4 of 1/4. Well, we know that's 1/16. And then the next piece is 1/4 of 1/4 of 1/4, so that's 1/64. And dot, dot, dot. So this is actually a geometric series, right? It's a geometric series where my R equals what? Yep, 1/4. Okay. And that guy is less than 1/4, so we know the formula for that. We would use it really quickly and easily. S equals. Now the weirdness about this is, what is my A1? Because I need that, because remember the formula is A1 over. So the A1 here, yeah, A1 is 1/4. And the R is 1/4. So it's kind of a little interesting. We have 1/4 on top over 1 minus 1/4, right? So this is 1/4 over what? 3/4. And then, hang on, we've been dealing with this. We know what that's going to look like. I need to get rid of the 3/4 on the bottom. Everybody say what I'm supposed to multiply by. 4/3, 4/3, bottom goes away. What the heck happens on top? Yeah, those 4s are going to reduce also, right? So this is just 1/3. So what weirdness happens is, even though I'm taking out a 4th every time, you can kind of actually even see it if you look inside of here. This sequence that's going on in the middle here is actually the same as this sequence that's going on the bottom, and it's the same as this sequence that's going on the top. So if you can physically see that, then hey, I can kind of see I'm taking out the middle third, right? But that's not what you might have guessed from the beginning if I had asked you, right? So kind of some interesting stuff going on in there. Come back in a minute. I'm going to give you a housekeeping video. And that's about it for sequences and series. So, I'm sorry this week's so long, but we fit it all in and we're ready to review and take a test next week. And I know you're all thrilled about it. So see you soon for housekeeping. All right.